Okay, so let's go back because it's been a few days. You know, it doesn't really matter the type of things in the list, and we can use a for loop to iterate over a list really easily, just like we did with a string, you know, because the for loop really is for each thing in a collection of things. So here I'm using it for thing in collection of things, where collection of things is the list. And if I print it out, the first time we see hello, and then 10, and then true, and then 100.001. It works the same way, it's just, it goes through the collection one at a time. It's just this time it's not a string, it's a list. And we saw that lists were in fact mutable. Strings weren't. With a string, we could change what, if we had a variable a referencing a string, we could change what that variable had, but we couldn't go to the string and modify that string itself. We couldn't change something about that string. We can with lists. And then we saw range. Oops. It's a great way to just have a list go some number of times. Now what's interesting is range is kind of like doing this. Right? It's a collection of things, except I just wrote range. But it does the same thing, which is pretty neat. Makes things a little easier instead of having to write out the whole collection of things you want to iterate over. All right. So now let's say I was doing that linear search. But this was the version of the linear search where first and foremost we're doing it on lists, not strings. Where now I'm looking for some arbitrary thing in a list as opposed to a letter in a string. And I don't just want to know if the thing exists. What I want to know is where, what index does the thing exist at if it exists? And if it doesn't exist, I'm going to return -1. So here's the problem I have. When I'm using a for loop, to be clear, this is a minor problem, but I'm using this problem to motivate something neat. This is a very minor problem because there's a lot of workarounds for this. I want to know the index of where the thing is. But based on the for loop doesn't care about indices of the collection. The for loop only gives you each thing in order. But how do I get the actual index of that thing? With the while loop, I had that counter, right? And that counter started at 0, then it went to 1, then it went to 2. And I could use that counter to index the list or the string or whatever it is. Here, I don't have a counter. I've just got the element. If the current element is the needle, how do I get to the index? Now, there are a lot of ways I can go about solving this. To me, the most obvious is this. I'll create some and this should do the trick. I just created a counting variable to keep track of the current index. Every time I go through the loop, you update it. And if you're thinking, how would I have known to have done that? You're not supposed to know to do that. You just go, well, what do I need? I need something to keep track of the current index. Make one. Make a variable to do that. There, that's how I knew to do it. So that's one way to do it. But now, there's nothing wrong with this. This is, of course, correct. This is working. Or maybe we could do it like this. Well, actually, before I show you another option is, when you look at this, you go, I mean, this is kind of like I'm losing the benefit of the for loop. The benefit of the for loop was like how it was like the syntactic sugar of how nice and easy it was to write the for loop. This is almost the same as a while loop now. I mean, look, it's basically and then I guess I would have to do haystack at there. But like, oh, I'm missing my colon there. And there's nothing wrong with this. This is entirely correct. If you submitted this on assignment, I'd be very happy with that. But, you know, we're kind of losing the whole, like the niceness of the for loop, the nice syntax of the for loop. So an alternative would be, okay, we could still use the for loop, but instead of creating this like external variable, maybe what I do is for I in range len of haystack. So this will take the length of the haystack and have the loop run from 0 to the length minus 1. And then I would do and then I guess this would just be I. There, like that'll work too. But again, now like for I in range of the length of the haystack, I mean now I'm starting to like, I'm losing the nice syntax, which was kind of like the point of the for loop, you know? So again, there's nothing wrong with this. You submit this on assignment, you write this on a test, I'm very happy. This is perfect, this is great. But if I'm going back to the original, what I had, like this is what I want. And then in order to make this work, I wanted to use syntax that was nice like this. But in order to get this to work, I started to have more and more code, which there's nothing wrong with. But because this is such a common pattern, I want the value and I want the index that that value is at. We have another special keyword. And here it is. No, I can never remember the order. I think it's this. I could have them backwards. We'll find out in a second. Perfect, looks good. I use this enumerate keyword. Now what's neat about this, when I use this syntax, notice, pay very special attention to line 2. For I, now again, I could be whatever. I could be, let me change it to index. Now I is often used, by the way, to mean index. For I, comma, element. So enumerate the thing. So what this will do, let me make it more explicit. Look at what I get when I use like the length of the range of the thing. This list is 0, 1, 2, 3, 4. It's 5 long, so the loop ran 0 through 4. We see the indices only. But that's fine because I can get the value at an index by just saying at index I. Right? I can print out, okay, I've got I and then something at that index is A. Right? If I just do in something, I just have A, B, C, D, E. But I have no easy way to get the index of that thing, other than what I had shown you moments ago about the variations on how we could do that. Now, here, we get I and E, and they are two separate values, but the first value, I, corresponds to the index, not because it's called I, but because it's the first one. And then the E, I just called it E, that is the element at that index. Of course, everything I showed you were all variations. Like, I use different code to do the same thing for that linear search or for this like print, basically. I'm just showing you the different syntax. And this enumerate is just more syntactic sugar for a nice and easy, clean way to loop over some collection while also getting the indices that you're currently looking at as well. Or like, you don't have to think of I as an index. You can think of it as how many times did this loop run, right? This is the 0th time, the first time, whatever. There's a counter along with the current element. Cool? I think this is cool. Any questions about it? If you hate enumerate, you don't ever have to use it. Fine, great. You can live your life by never using this. If you like it, great. Go ahead and use it all you want. I think it's cool. Any questions about it? All right. Yeah, this is just going over all that. Great. Any questions about any of that before I move on to the next topic? And I have a feeling the next topic is, yeah, you're going to love it. Last chance for a question before I ruin your day. Okay, so I've been lying to you a little bit about some of the stuff we've been learning about. And I'm about to get honest with you. I'm about to explain how some things work in a little bit more detail. Now, there's a warning there, and the warning is, there's a couple of warnings I want to give you. One, this is going to annoy a bunch of you, what I'm about to explain. This topic is about to annoy a bunch of you. But I promise you, I've never actually misled you. It's just, it'll seem as if I had, but perhaps I could have been clearer on some differences up until this point. But there was a reason I wasn't clear, because I didn't want to confuse you. Now I want to confuse you. But trust me, it's actually not that wild. Just bear with me. I'm not telling you this because I want you to get all worked up about it. I'm just telling you, I'm about to throw in a wrench probably into some of your understanding and some of how you've thought of things already. The way I'm about to explain the following is going to be at like a 1,000-foot view. It's going to be fairly high level. There are some nuanced differences and details that I'm going to skip over that are honestly not that important to get the intuition and the important ideas I want to cover in this topic. I am not setting this up by saying the following is hard. It is not hard. Not at all. No, 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 no. It's not necessarily trivial, but I don't want you to start listening and be going like, oh, here we go. I'm going to have to work hard to understand this. No, 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 no. All you have to do is just follow along, and perhaps you might have to break some of the things that you thought worked a certain way a little bit in your head. And even weirder, some of what I'm about to say is not really true in Python, but is traditionally true. But Python actually pretends to work the traditional way, when in reality it actually doesn't at all. It just pretends to. So there's a lot of detail there, but that's not important for right now. We're going to talk about references. it is very important for us to know and understand what's been going on with our variables and what the variables are actually holding on to, what data they have. Nothing I've told you so far has been incorrect. And everything I'm going to tell you is going to be consistent with everything I've told you before, but there's a big thing that you may not have really, that hasn't clicked yet. And here's another note. Typically, when referring to memory addresses, there might be one person in the room that cares about this note. Otherwise, you can ignore it if you're like, what? Typically, we would refer to memory addresses in hexadecimal, which is like a base 16 number, not a base 10 number like we're used to. But for simplicity in this topic, I'm just going to refer to them as decimal numbers, just for ease. Okay, here is an idealized view of memory on your computer. I hope you like my Microsoft Paint. What we have is just like a big table, all right? Each spot in that table has its corresponding memory address. That's the green label, right? I've got 124, 125, 12, and so on. And you could pretend this goes on forever. And by the way, I want to make sure this is a very important topic. Y'all should probably, you really need to listen to this one. There are some topics you zone out on, fine, but this is an important one. Because this tends to be something that a lot of students get tripped up on, because I think they're trying to skip some steps. But they're working too hard, they're going too fast, slow it down, keep it simple. But this is the idealized view of memory. I could think of it as each seat in this chunk of the lecture hall, right? And each of them have an address, right? 12, 13. Right? So they all have an address, they all have a seat number I could refer to. So you're all data in memory right now, all of you sitting here. All right? What else? And yeah, so we store our contents in there. And traditionally, we use 4 bytes to store what we call the primitive types. And you might remember me talking about primitive types. Those are your things like characters, integers, floats. Booleans are a little different, but whatever. They've got, we know how much room it takes to store an integer. So we could actually even think of all these memory addresses. Really each of these memory addresses could be broken down, maybe each address corresponds to 1 byte of information, but we actually have 4 bytes. But for simplicity, we can think of this as being broken down such that I can fit an integer nicely into one of those cells. How I break it down is entirely arbitrary, but I can fit an integer nicely in one of these seats, in one of these memory addresses. I can fit a character in there really good, a floating point number in there really good. The computer is really happy with that. So, okay. So let's say I have an integer called x. What its actual value is it doesn't really matter, but it's a primitive type, and traditionally we're using 32 bits, that's 4 bytes, 8, 16, 24, 32, 4 bytes to store an integer. So that's a series of 32 zeros and ones, and there's an example of one that just happens to be that number, whatever. Each of those zeros and ones is a bit. A group of 8 of those is called a byte. All right? Does anyone know what we call a group of 4 bits? This isn't a joke. Does no one know, really? That's sad, because it's fun. It's called a nibble. That's not a joke. It is. They call them nibbles. Because it's not a byte, it's a nibble. Anyways. So since we know how much memory, how much room an integer takes, I can divvy up my RAM nicely, and we can create an integer variable like x equals 17, and then something like this will happen in the computer. By the way, the actual memory addresses I'm using here are entirely arbitrary. If I go type x equals 17, the computers are going to go, all right, I always go to memory address 126. No. This is just, they're arbitrary. But when I show up and I say x equals 17, the value 17 from the operating system gets assigned to some memory address in the 32-bit chunk of memory, 4-byte chunk of memory. And a label x is created for that memory location. So I have the variable x that is going to be memory address 126. So whenever I want the value stored in x, the computer goes, oh, x, okay, that was stored in the memory address 126. I'm going to go look it up. Oh, it's the value 17. That's what's happening. So far, so good? This is the simple part. Now, pay close attention, because what I'm about to explain is probably what you've assumed so far, which is good. If I come along and I want to make a copy of the value stored in x, right? I want to come along and I want to copy the value stored in x. I want to come along and I want to write y equals x. All right? This is what happens. The computer goes to the memory address associated to x, which is, I think, 126. It makes a copy of those contents, which is the value 17. The operating system will then decide on another memory address that we're going to store the copy in. And in this particular example, it just so happened to pick memory address 129, again, entirely arbitrary. It takes the value from where x was, 126, makes a copy of the contents of that memory address, and puts it in a new memory address, and then assigns a label. Okay? Any questions so far?
Is the assignment random always within the 32-bit section? Like, even though those are arbitrary values, is it just wherever?
It's not going to be random, but it's definitely not going to be something you're ever going to really care or think about, right? If, you know, it's actually kind of interesting. I'm going to show you something neat here. Anything like you create, like if you might write a function, that function also has to get stored in memory somewhere, right? So this is an aside to kind of hit your topic. There's something that's a little interesting you might find. So, you know, if I want the result of ASD, I'm calling the function ASD with 1 and 2, and it gives me the result. But how many of you, and I'm willing to bet at least half of you, have accidentally called a function, oops, they tried to call their function, but they never actually called their function. They just like printed out the function, not a call to the function, like this. And you see something like this. Raise your hand if you've ever seen something like that. Exactly. A lot of people make this mistake. I do it every once in a while. Function ASD at OX7F995D015E10. That's a memory address. How it got picked, I don't know. That's up to the operating system. It's not my issue. But that's actually telling you the actual like memory address of where that function is stored in your computer, which is pretty neat, I think. In some programming languages, we have a lot of control. We have a lot more control over the memory at a very low level. But you don't really see that anymore because everyone realized, you know, we don't want to deal with that. That's someone else, that's the operating, they're going to deal with that. And it ends up being a big headache, a recipe for disaster. That's where when those types of programming languages are subject to being like hacked a lot more, there's a lot more vulnerabilities because of it. In fact, you know, raise your hand if you've heard of the state's NSA, right? So there's even like a document they posted recently saying like, stop using these languages, people. It could literally be like a national security issue because of how vulnerable your code is. So in other words, don't use those languages. In other words, it doesn't matter anymore. It does, of course, but let's pretend it doesn't. All right, back to this. So any questions about this? I said y equals x. The computer goes, where's x? Oh, well, that was the label for memory address 126. I go to memory address 126. The computer copies the contents of that memory address and puts it somewhere else. And then it creates the new label for that new memory address that it decided to put it in. The label is y because that's what we picked. Okay? Now, listen carefully. When I said y equals x, the computer, listen to what I'm saying very carefully. Y equals x. The computer copies what's stored at the variable x. It copied the contents of that memory address and put it somewhere else. So it copies the contents of what's in that memory address. Everyone say it with me. It copies the value at that memory address. So you've all said it, so you understand, right? So far, so good, though. This shouldn't be mind-blowing. And I'm not doing that to belittle you. I'm doing that because I know half of you, despite saying it, are going to come to my office hours in a week and be like, so it works totally different. You said, and I'm going to say, no. I made you all say it, and I've got it on video. So just listen carefully. It copies the value stored at x and put it somewhere else. Okay. Now, objects. Objects is that word I use to describe not primitive types, basically. A string. A string is an object. A list is an object. And one of the issues with these things is, how do I store a list in RAM? Anything I want to store on the computer, it's got to be in memory somewhere. So how am I going to store it? Do I put the list in one seat? Well, that's not, I mean, it depends on how big the list is. If the list has 7 integers or 700 integers, the one with 700 is probably going to need more space, right? But how am I going to manage this? I can't put 700 integers into one seat. We got a funny little problem here. So this is where the idea of references comes up. So here is a list of length 8. The contents here, for demonstration purposes, are labeled A through H. Don't think of them as the letters A through H. They are just some arbitrary values. You can think of them as integers for the sake of argument here. They don't actually have to be the characters A through H. It's just they're some value. All right? In the above examples so far, each chunk of memory that I showed with the address, I was saying is like divided into 32 bits, which is enough space to store one integer. Unfortunately, I've got 8 integers. So I need 256 bits to store all 8. So if I need 32 bits to store one integer, I need 256 bits to store 8. But each of these only has 32 bits. So we can see the problem. 256 is bigger than 32. I can't shove 256 bits into one spot which can store 32 bits. But fortunately, we have a simple solution. Here's what we do. Store each value in its own memory address. Similar to how we stored 17 in a memory address. And we're going to section off a chunk of RAM, a chunk of memory, for that content, for that data. Like this. So I come along and I want to make the list with the values A through H, whatever they are. So the computer's going to go find a chunk of memory that has enough room to store those 8 pieces of information in contiguous RAM. Now, it doesn't have to be contiguous, it's a whole thing, but for simplicity, I want a section of 8 seats that I can store my list. Index 0, index 1, 2, 3, 4, 5, and so on. Okay? So, and it just so happened that this list started at memory address 677. I put A in there. At 678, I put B. 679, I put C, and so on. So far, so good? It's as if I created 8 variables for integers, stored it in memory, put them in memory, and somehow they were one after the other. Right? That's all it is. Each of those cells, each of those memory address locations could store an integer, so I need 8 of them. Just put there. Take 8 in a row. Boom. There I've got my list contents. All right? Any questions so far? I keep, yes?
I'm just wondering, I guess, if you have a really big integer, say like, I don't know, 6 million or something like that, would it still store in a single?
So there's a lot of, it depends on the programming language. So there are ways around it. In Python, so here's an aside. In Python, everything's an object. So everything actually takes up a massive amount of space. So you could have hilariously large integers in Python, it's fine. If you're dealing with a programming language like Java, like we will next semester, if you use the wrong type and you try to put a number like 7 trillion in a 32-bit number, Java will ignore all of the bits that overflow and just store whatever the remaining bits would be, meaning it wouldn't be 7 trillion. It would be whatever that number is if you only look at the bottom 32 bits. But this all depends on the programming language and a lot of different things. In Python, there's ways around it. Just you could have huge-ass numbers, whatever, it's fine. But in other languages, you just have to be careful. You have to maybe specifically tell Java, here's a number, and it's going to be a really big number. So you need to make sure you can deal with that. Otherwise, by default, it'll only use 32 bits. Yeah. And we can have more fun with that next semester, because you're taking 162, right? Yeah, we're going to have a lot of fun with that. So, other questions? Good question, though. You're thinking about this stuff. That's good. Yeah?
Are only objects stored with addresses?
Everything is stored. Well, maybe I'm not sure on your question. Everything is stored in RAM, right? If it's a single variable, we just throw the variable in RAM. You know, all of that data is stored in a memory address. So everything is still going to be stored in RAM at some memory address. But maybe hold on to your thought, because I think we might answer it in a moment. If not, ask it again and we can figure it out. Other questions, though? So now, of course, showing you this, I've just stored the contents of that list somewhere in memory. That's all. We need to keep track, though. Like the computer needs to know, Python needs to know, like the computer said, all right, I'm going to store that data from memory address 677 to 684. But Python needs to know, well, okay, so the computer went and put that data somewhere, but where is it, right? Python knows I've got the variable x, and the computer put that in memory address 126, so whenever I need the variable x, I just go look up what's in memory address 126. Why? It was 129, right? So whenever I want y, Python knows, okay, I got to go check out memory address 129. Here, the way I've shown it, I've assigned A, B, C, D, E, F, G, H in memory, but from what I've described so far, I haven't really talked about, well, how is Python going to know where that is? And this is where the magic happens. So I come along, and maybe I want to make the variable, okay, z equals A, B, C, D, F, G, H, right? Given the above list creation, the computer finds a contiguous block of memory to store the contents. Each element fits nicely into the divvied up chunks of RAM. That's what we have so far here. Okay, we put that data in some chunk of memory. That data is in memory. Then, the information needed to find and access where on earth that list is going to be stored in a piece of memory labeled with the variable z. Why z? Because that's what I picked here. All right? So this ends up being how it happens. When I had an integer x, the value stored in that memory address associated with x is the integer 17. When I had the integer y, the value stored at the memory address associated with y, which is 129, stored the value 17. But with a list, it's a little different. Because the contents of the list, the data, the values in the list were stored in memory address 677 through 684. But the variable that knows that is actually memory address 131. Again, arbitrarily chosen. It doesn't matter really where. But notice what is actually stored at that variable's memory address. It's not the data. It's not the list. The list is not stored. None of the data that I want in that list is stored in memory address 131. It's not. It's stored at memory address 677 through 684. The thing that is stored at memory address 131, which is associated with Z, is the information I need to get to the data I care about. It's a reference. It's not the data, it's a reference to where I can find the data. All right? This is where where students tend to find things are getting weird. It's kind of intuitive why we did it this way, and I'm giving you the explanation of how things come together. But where are your questions now? The key thing to note here is the data that I stored was over there. The data stored in the variable z, and again, to emphasize, the reason it was called z is because I just arbitrarily picked z. Z equals that list. The data stored at z is not the data in the list. It's the information I need about the data in the list so I can get the data from the list. Okay? So this is the idea of a reference. Z, x stores the value 17. Y stores the value 17. Because I made a copy of the contents of x. And I copied the contents stored at the memory address associated with x and put it somewhere else. Now here with z, z is not the list. It's not. No variable is a list. A variable could reference a list, but it's not a list. This is an important concept, especially because of the following. Oh, yeah, here's a quick thing. I know I've already spoiled this for you, but maybe if you weren't paying attention before. So in this particular example, I'm showing you there would be more information stored with Z, where I can find the list, how long it is, and maybe some other properties about the list. But for our purposes here, let's just say it's the start of the list. Based on how this image looks, can you make sense of why we index starting at 0? What's that memory address 677 plus 0? The A. What's that memory address 677 plus 1? B. The indexing is the offsets. It's like doing like that memory arithmetic, right? Go to the start of the list and take 0 steps. Take 1 step. Take 2 steps. That's why, counting at 0. All right. Now, hold on to your hats. So, if we want to make a copy of Z, like we did with X and Y, I would write something like W equals Z. And the computer is going to listen up. W equals Z. What the computer is going to do is exactly what it did before. No difference. No difference. And this is what's going to piss a lot of you off, because later you're going to come to office hours or get mad at me in lab saying, you said it acted the same, but it's not. It is. I'm not lying to you, I swear to God. When I say W equals Z, the computer is going to come along and do exactly the same thing it did with Y equals X. It's going to go to the memory address associated with Z, copy the contents of that memory address, put them somewhere else and give it the label W, because that's the variables I picked. So just like before, when I said Y equals X, the computer went to the variable X, copied the contents of that memory address, and put it into Y. Here, W equals Z, the computer is going to go to the memory address for Z, copy the contents, put it into W. But the difference is, and this is not a difference in what the computer is doing, it's think about what was actually stored at Z. Z was not a list. It was a reference to a list. So when I make a copy of the contents of Z, I'm making a copy of not the list. The list is left alone. I'm making a copy of what's in that memory address. And what's in that memory address is a reference. So, if I were to say W equals Z, this is what happens. When I wrote X equals Y, no, Y equals X, it made a copy of the contents of X. How many values of 17 do you see in this picture? 2. Because when I copied the contents of X, it copied the value 17. How many references to the list do you see in this picture? 2. Because when I copied the value of Z, it copied what was in there, which was the reference to the list. But how many lists do you see in this picture? 1. Here's why this is so goddamn important. This is the big thing. Now, really hold on to your hats. If I went to W and I said, hey, W, go to index 4 and change yourself to be a P. Okay? Nothing crazy. Go to index 4 and change the value at index 4 to become a P. So what's the computer going to do? The computer's going to go, okay, well, what's W? Oh, okay, well, W, that's the memory. Oh, that's a reference to a list. So go to that list. Go to index 4, 0, 1, 2, 3, 4. Change that E to a P. In fact, let's do this. All right? I've got the list A, B, C, D, E, F, G, H. Here I actually made them the strings, A, B, C, D, F, G, H, for demonstration purposes. And then I said W equals Z. And based on what we know, how many lists do I have based on those 4 lines of code? Everyone say 1. But how many references to that list do I have? 2. So if I come along and I say, okay, W at index 4 equal P. And then I say, okay, print W. So far, so good. Here, I'll get rid of these prints here. I said W at 4 become P, and then I print out W 0, 1, 2, 3, 4. We can clearly see it's a P. Right? Yeah? Raise your hand if you're happy. Put up your hand. I want everyone to be happy. See, I knew it. You're happy. Who wants to potentially be unhappy? What happens if I say this? What are we going to see printed out if I print out Z? The same thing. This is what pisses people off. If you expect, I've explained to you, hopefully I gave you the intuition as to why this worked the way it did. There was only ever one list, but I had 2 references to that list. And through one reference, I modified it. But there was only ever one list. So when any of those references, I need a volunteer. Someone put up your hand. I want someone, okay, over there. Put up your hand and leave it up really high. Okay. Every single person in this room, point at him. Right now, we've got a few dozen references to the one. Let's pretend you're all just references and there's only one human in here. All right? And I'm pointing at you as well. And I'm going to tell you, lower your hand. Hey, what happened to that person you're looking at? There was one person. Only one of the references had to give him an instruction. But every single person looking at him, he changed, didn't he? Something about his state changed. He lowered his hand. There could be a billion references to one thing. If any of those billion references make a change to that one thing, it's going to change for everybody. Are we out of time? Oh, thank God I ended when I did. This is a big one. I want you to ponder this really hard. Okay, here's the final note. In reality, in Python, the values won't be stored in contiguous order. It'll actually be a series of more references. That'll then be stored in who the hell knows where. But that doesn't matter right now. There, we're done the topic. Well done, everybody.